SwayamPrabha. Digital India. Educated India.
सहनावतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, this will be lecture for number 49 in our ongoing series on mechanical measurements. We are actually going to have two lectures which form module 5 and the last module. So, the two lectures will look at some general issues that are important in measurements, which have been considered in some small detail as we went along the course of lectures, but I would like to highlight some of these things which are important in any measurement practice. So, let us look at the things we are going to discuss. The issues which we are going to look at are the discussion, the data acquisition, data manipulation, data presentation. Of course, we have been referring to some of these as we have discussed many different ways of measuring different quantities, but here we will try to generalize to some extent and discuss the important things which we should know. Then I will also look at case studies pertaining to the design of experimental setup. It is not like designing of the experimental design of experiments we have seen earlier is to determine how many experiments we have to do for a particular study, but here we are talking about the experimental setup itself, and we will take maybe one or two examples as it becomes possible. The case studies will talk about the layout, selection of the instruments, and also to some extent the aspect of design of experiments. So, I will go back to one of the earlier slides which I showed at the very beginning of the lecture series, and that was the sketch showing the general measurement scheme. The general measurement scheme consists of, as you can see here, the detector and transducer. This is the heart of the measuring scheme, the detector and the transducer, and the signal from the detector is conditioned before it is communicated to the computer or to the display unit or to the controller, as the case may be. But you will see that between the detector and the user, if this you consider as the user or where the information is going to be looked at in detail, there is something called the signal conditioner, and that I have shown with a white background here. So, we will be discussing some of the important features of this particular thing, the signal conditioner. So, we have an input coming from the detector and the transducer, which is in the form of an electrical signal, and I have an output which is in a form suitable for being communicated to the computer. This is the entire thing which we are going to look at. Between the input and the output, we have what is called the signal conditioning circuitry. What it does is it changes the input level to the desired level at the output by either increasing the value or decreasing the value, that is by amplifying or reducing the amplitude or the signal magnitude, or it may also manipulate in many other ways by, for example, by taking the logarithm or integrating the input or differentiating the input and so on and so forth. So, these are all possible conditionings which can be done. Many times the detector signal is very, very low and it needs to be amplified to a larger, to a suitable level, so that it can be communicated to the computer or the display or the user in general. So, we will look at the signal conditioning and see what are the things involved. The signal conditioner, what it should do is to transform the input to a level desired at the output here by using some external power. It should not draw any power from the detector. The detector itself should not be loaded. That means that no current or no excessive power should be taken from the detector. So, the idea is to condition the signal using external power, which will actually supply the power required for this transformation from one level to the other level. So, let us look at the type of things one would like to do in signal conditioning. I have just labeled a few of them. One is of course amplification, where the magnitude of the voltage or the current or whatever signal we are getting is too small. We would like to make it bigger by amplification. It may also be amplified after some manipulation, like multiplying by a factor or by taking the logarithm and things like that, what we mentioned earlier. So, some manipulation may also be done. For example, we may subtract some particular factor out and then amplify it and so on. Invariably, we have in the modern practice a conversion of analog signal to digital signal, because most computers and most display units nowadays will use digital form of signal. So, digital analog to digital conversion is an important part of this signal conditioning. In the digital form, it can be communicated to a computer, and the computer can also put it into a data storage, which can be retrieved for later use or later analysis using appropriate software. So, I have mentioned here manipulation using software. There are some useful softwares which are available now. One is MATLAB, the other one is LabVIEW. LabVIEW is specifically specifically useful for signal analysis, and then Excel, for example, which can be used for plotting and things like that. So, these are all softwares which are useful in processing the data after it has been gathered or after it has been communicated to the computer and maybe stored in a data storage. Then we can use some of these things. In fact, LabVIEW can be used as a virtual instrument, that is what it means, laboratory virtual instrument, that is what it stands for. So, we will be using some of this software for doing the job. The software can be used only if the signal is available in the digital form. So, this analog to digital conversion is an important aspect of this signal conditioning. Let us look at some of the simple things which we should know in using these instruments in the laboratory. The first one I am going to discuss in some small detail is the amplifier, which is very useful in increasing or improving the signal size. If the signal is very weak or very small in magnitude, I would like to make it much bigger, so that it can be communicated to an external device. So, an amplifier is basically an instrument to which I input the input signal. This is the signal V in, and it will amplify the signal to a value V out, and the gain is shown here as G equal to V out by V in equal to, it is simply determined by the values of these resistors RF and R1. This is the feedback resistor, and this is the input resistor R1, and the amplifier itself is some kind of a black box for us, which draws power from an external supply. We have a positive and a negative supply. Usually it may be plus 15 minus 15 volts, or plus 12 minus 12, or sometimes it may be 5 and 0, or 5 and minus 5, things like that. So, these are possible values. So, what the operation amplifier does is to give a magnitude, they give a gain which is purely determined by these resistors which we choose in this fashion here. So, let me just digress here and discuss some of these in a very summarized fashion on the board. So, we are talking about an amplifier and I just want to look at the fundamental or basic features of an operational amplifier. So, the operational amplifier is the heart of the signal conditioning system, and what the operational amplifier does is, one, does not load the sensor. So, it draws no power from the sensor or very little power from the sensor, amplifies the signal using external power. This is very important. And in fact, I can represent the amplifier in a very schematic way in the as follows. So, usually it is given by this triangle shaped symbol. This is the amplifier. We will call it the operational amplifier, op amp for short. And I have actually two inputs, one which is called the inverting input and the other one is the non-inverting input. And there will be a positive power input and the negative input there, and there is an output terminal. This is the output. So, we have two input terminals, and if you look at these two input terminals, it is like, suppose I show it in terms of a resistance between these two terminals. This is extremely high, extremely large. So, we say that the operational amplifier has almost infinite input impedance, number one. Number two, the operational amplifier also has a very large gain, that is, if you do not connect anything to the terminals, the gain may be something like 10 to the power of 5 or more. And the consequence of not having a very extremely large input impedance is that if I show a terminal here, another terminal here as an inverting and non-inverting terminal, essentially they are at ground potential. So, plus and minus are at the ground potential or at the same potential, because there is no current or very small current, because the extremely large value for the input impedance means that the current through this is very small, negligibly small. Therefore, we can say that these two are essentially at the same potential. So, in fact, based on this I can do a simple analysis, and let us see what happens if you have a what is called a differential amplifier. So, this is the differential amplifier. Most students in electrical engineering will learn this in their regular classes, but the mechanical engineers are not usually exposed to some of these, and therefore, it is necessary to discuss some of these in this particular set of lectures. So, we have a resistor, another resistor here. So, we will make these two equal to R1, and this is the input negative, this is the input positive. So, I am connecting the positive input to this and negative input to this. Therefore, these are two potentials, these positive and negative are with respect to the ground. So, the ground is here, I will show it like that, and there is a resistance R2, and here there is one more resistance R2, and this is your output. So, let me just say what happens. Suppose the potential here is going to be V minus and the potential is going to be V plus, and we know that V minus is equal to V plus. Both of them are equal. So, this is the assumption, because there is no current through these two terminals. Now, you can see that if I do an analysis of this circuit here, very simple, you can see that the current through this resistor is nothing but V1 V in minus V minus, that is the potential difference, divided by R1. This is the current through this, and because there is no current through this, as far as this node is concerned, whatever current is enters here, it has to leave, the current should be the same. So, this should be equal to V minus minus V out divided by R2. So, this is one equation for this, and now you can do the same thing here, because there is no current through this, whatever current comes here must go to the ground, and therefore, you can write the other expression as EV in plus minus V plus divided by R1 is equal to V plus minus the ground is 0 divided by R2. And you notice that I am going to make V1 equal to V plus in this V minus equal to V plus in these two equations, and then we can simply manipulate and get the following expression. I will leave it as an exercise for the student to accomplish. So, we can see that V out will be simply given by R2 by R1 into V in plus minus V in minus. So, this is a differential signal, and this is the gain of the amplifier given by the resistance ratio R2 by R1. A simple analysis which shows that we can use this as a differential amplifier, because it is the difference between the voltages applied, as you saw in the figure here, that the difference in voltage which is going to be amplified, and the output voltage is simply given by the difference in the voltage here multiplied by the gain which is given by R2 by R1, which is simply the ratio of the resistance. So, before we go ahead, let us just look at what are the things which we can do. In fact, the gain could be quite high. Easily we can have 10 to 100 gain without any problem. And if you want a large gain, suppose the input signal is only microvolt range and you want to make it millivolt or even higher, you require a gain of 1000 or more. So, in which case we can use, instead of one single amplifier, we can use say one amplifier followed by another amplifier, so that the amplification can be done in stages. That is number one. Number two, if you look at this carefully, sometimes what we do is we simply have what is called a voltage follower, which is a unity gain amplifier. That means that what is the advantage of that? If you have a unity gain amplifier, the input impedance is very high. That means it does not take any current from the sensor, but the output it can give you sufficient current for driving some external circuit. So, sometimes we can simply have a unity gain amplifier which will give you a capability for supplying larger current, but not without loading the input or the sensor itself. So, these are some of the things which one can do. And let me just go back to the presentation and show you many more things which can be done, and this is exactly what we showed just now. It is a basic inverting amplifier. What I showed was the differential amplifier. So, you can see that if the V1 and V2 are the potentials here and here, so this gives you minus R2 by R1 into V1 minus V2, which is the same form which we obtained in the board. So, the output becomes an amplified value of the voltage difference. Now, there are many other issues also, we will come to that. Before we do that, let us take a look at one or two other variations of this. So, you can also have a summing amplifier. For example, if I have several voltages to be added together and amplified to a larger value, I can connect like this V1, V2, V3. If you remember, we did that in the case of a set of thermocouples. We wanted to average the thermocouple readings. So, we were actually doing that. Similar arrangement was shown there. So, we have V1, V2, V3 etc. are connected to the non-inverting, the inverting pin of the amplifier, and there is a feedback resistance RF. Again VCC and V minus VCC are the plus and minus positive and negative power supplies. So, you can see that the output is now given by minus RF into V1 by R1 plus V2 by R2 plus V3 by R3. So, if I make R1 equal to R2 equal to R3, all these are going to be summed and amplified by the same factor. So, summing amplifier you can also sum by either with the same amplification or different amplifications you can have for different signals. So, that is what it shows. By choosing R1, R2, R3 suitably, you can manipulate the signal. The variation which is shown here is an integrating circuit. Suppose I want to integrate the input voltage with respect to time, all I have to do is to connect the RC like what is shown here. This is the capacitor and the resistance. Choose these values properly so that you get a V out equal to minus 1 over RC. RC is the time, the product of this, and the integrated value is going to be the output. And similarly, a differentiating circuit is also possible if I just invert the C and the R, the capacitance instead of the resistance and resistance instead of the capacitance, you get an expression like this: V out equal to minus RC d V in by dt. There is the derivative of the input signal. The other point is, in any measurement where you are going to look at signals coming from a sensor, we also have a little bit of noise in the noise accompanies the signal. In fact, we have already seen in our discussion earlier that all measurements are prone to errors, and we discussed some of these errors. These errors could be in the form of a noise which is present along with the signal, and if the noise is very large compared to the signal, it may be sometimes not possible to find out what is signal and what is the noise. Therefore, many times we have to suppress noise or eliminate this noise. I will take one or two simple examples only, because we do not have too much time to do that. Suppose we have an amplifier which is amplifying an AC signal. An AC signal is being amplified. So, you know that AC signal consists of some kind of a periodic signal like this, and it will contain all different frequencies. And you also know that we use usually a 50 hertz source. Our electricity system supply is at 50 hertz, and many times what happens, the instrument or the amplifier is close to the electrical line, in which case it will catch little bit of this 50 cycle noise. So, 50 cycle noise, 50 hertz noise can become a problem. In for example, in radios and televisions, for example, this noise will be appearing as a hum. In audio amplifiers, 50 hertz becomes a hum. You get that background noise which is annoying to the person who is listening to the music or speech or whatever. So, one way is to not allow this 50 hertz noise to corrupt your signal by following proper wiring practice. We use, for example, coaxial cables, so that you have the cable is in the form of a wire surrounded by a shield, so that the outside noise does not get transmitted to the wire, because the shield will not allow the 50 hertz or whatever noise to corrupt the signal. So, that is one way of doing it. Of course, with all this you can only minimize, you cannot really eliminate. So, the only way of doing that would be to use a proper filter. Filter is something which is going to remove unwanted stuff. So, this is remove unwanted signal, unwanted noise. So, in this case I am talking about 50 hertz noise. If I have an AC amplifier and if I am looking at signals which are at a sufficiently high frequency compared to 50 hertz, what I can do is I can use a filter which will remove low frequency part of it and only pass the high frequency. So, we have what is called a high pass filter. So, we can use a filter which allows frequency much larger than 50 hertz. That means that the signal it is also a part of signal conditioning, as you can see. We are trying to remove the unwanted oscillations which are taking place at 50 hertz by doing this. So, this can be done by using what is called a filter which allows only high frequency signal to pass through and the low frequency is removed. So, let me just show you how it is done by looking at the picture here. So, we have a filter here. Do not worry about the bottom portion, I am just looking at the top portion here, a high pass filter. You have an R, another R here and a 2C. You know that if the frequency, if the impedance of this, it is actually the impedance of the, when you have an AC signal passing through, the impedance is the one which is going to modify the output input relation for a filter like this. So, in the case of a high pass filter, the high frequency will pass through and low frequency will be bypassed through the and go to the ground. That means that what is going to come out is only the high frequency signal and low frequency will be filtered out. In this case, what I have done is I have taken what is called a RC notch filter. It is also a twin T. The twin T is because there is one T here comprising of two resistance and capacitance, and there is another T here corresponding to this with two capacitances and one resistance, and this is grounded here, and the input and output are connected here. The characteristic of this particular notch filter or RC notch filter is actually shown in the next. This is the filter, the low pass and the high pass, and then you have a summing amplifier. This summing amplifier is like what we showed a little while ago, and what you see is that the notch filter frequency response is like this. In this case, of course, it has been made for some other frequency, not 50 hertz. This is taken from some reference which was shown in the previous slide. So, what you see is that it allows frequencies up to this, and then at this particular frequency it blocks out completely. This is gain in dB, this is a logarithmic scale. So, it is attenuated to a large extent. Therefore, this particular frequency will be totally absent. If the noise is particularly localized at this frequency, you can have a notch filter designed with this as the frequency at which this notch is going to occur, so that you remove that particular unwanted signal of that particular frequency which is not wanted, and it will pass the other signal without any attenuation. And therefore, this is one way of. So, signal conditioning means removing unwanted noise or removing unwanted frequency components, passing only what is required, and maybe amplifying it to the extent, to the desired extent, and so on. So, these are some of the issues. And many times the instruments especially used in industrial practice also use what is called a 4 to 20 milliampere current loop. Let me just explain what it means. So, you have a sensor, it may be a temperature sensor, pressure sensor or any other sensor which we are interested in. The output of this sensor may be in the form of voltage or may be in the form of current, whatever it is. So, you have a transmitter. The transmitter, what it does is it takes the sensor output and modifies it to a current proportional to the sensor output, whatever the maybe the sensor. If the sensor is a pressure measuring device, the pressure signal is converted to a current. Okay. And in this case, if it is 4 to 20 milliamperes, it means that the maximum value of the current corresponding to 20 milliamperes will correspond to the maximum of the pressure signal, which for which that pressure transmitter, pressure sensor is designed. And the minimum will correspond to 4 milliamperes, not 0, because when the sensor does not have any output, it will still give you 4 milliamperes. So, that we know that the circuit is working essentially. So, why do we convert the signal from the voltage or whatever form it is to a current signal? That is number one question which we have to answer. Secondly, how do we use such an instrument? These are the two things we will look at it. If you see the way the measurement is done, I have the sensor here and the transmitter very close to the sensor. Usually these two are almost like in the same box or same enclosure, and the voltmeter or the computer or whatever I am going to use maybe at a certain long distance from the place where measuring the sensed signal. For example, in a laboratory, for example, the instrument itself may be mounted on some equipment which may be let us say tens of meters away from the voltage measuring device, or the cabin in which we have kept all the measuring instruments. So, the distance between here and here may be quite a large distance. Okay. So, if we were to, if the signal is transmitted over a long wire like this, there will be a potential drop, and therefore, it is not possible to transmit voltage signal over such long distances. It is simply not possible. However, if you have a current signal, the current is not going to reduce or increase, it is going to remain the same. The current is going to flow through this loop, that is why it is called the current loop. So, you see that it starts from here, the transmitter gives a current proportional to the sensor output, and then it goes through this, and there is a load which is located quite far away. The load is here, and across the load I am going to measure the potential difference. That means I am converting the signal which might have been originally a potential difference, I am converting it to a potential difference here at the user end, but I am using a current to transmit this information. So, the 4 to 20 milliampere current loop is a standard feature in many of the instruments, and what does it require? It requires an external power supply, a DC power supply, usually about 24 volts, it may be even 12 volts. The size of the power supply, or the potential, the voltage which the power supply should supply depends on the losses, potential difference, because of the current is flowing through this wire, the loss in potential due to the transmission through the wires, and also across this load resistor. Across this resistor I am going to measure the voltage. For example, I may want let us say 5 volts or 10 volts across this, and this resistor I have some particular value chosen such that it gives you 5 volts. So, this 5 volts plus whatever voltage drop take place in all these other wires and so on, that the power supply must be able to supply. That is the important thing. So, the power supply strength of the power supply is determined by the potential difference required here at the user end, and also the losses in the wires, because the current is going to pass through all the wires, and the sensor itself may require power, which is also drawn from this power supply. Actually, the sensor does require the power supply, because sensor voltage is sensed, or either the current, and then it has to be amplified or signal condition. The transmitter is actually a signal conditioner. what it does is to convert the sensor output into a 4 to 20 milliampere signal, which is what we are going to transmit over a large distance. So, you see that we have discussed 2 or 3 different ways of doing the signal conditioning. One was actually using amplification, and the second one we have looked at the current loop. Either way, whatever may be the method you are going to employ, finally we need to connect it to the external world, and that is done by usually using the following kind of arrangement. So, we have the sensor, which I can show as a circle here, and from there the signal is available, and the signal is now amplified and filtered if necessary, and so on and so forth. And then I still have an analog signal here. Because the sensor gives an analog signal. Now, I have to convert it to a digital form. So, I require what is called analog to digital converter, or ADC, and then this should be given to the output device. The output device may be a computer or may be a digital voltmeter, whatever may be the type of instrument. So, the input or the signal is analog, the output is digital, and this is communicated to an external device. For example, it may be a computer or a digital panel meter, also called DPM, or generally we can call it a digital voltmeter. Of course, in the case of the current loop, we can also measure directly the current using an ammeter. We can do that. That the one option which is already always available. So, this simply means that the output is digital, means I have to convert it from the analog form to digital form, and that can be done by using a suitable analog to digital converter. And let us simply look at some of the features of the analog to digital conversion process, because that is going to be important for the choice of the instrument and so on. And let us look at what this analog to digital converter means. So, you have an input range. For example, the signal may go from 0 to 1 volt or 0 to 10 volt or 0 to 3 volts, for example. These are all possible input ranges. So, I am going to convert this to digital form. Using a suitable ADC using a certain number of bits. So, let me just describe what this means. So, you know that the digital signal is always in the form of binary signal. So, it is a binary output. For example, I can take a simple A to D with a small number of bits to show what happens, just to understand what is going to happen. For example, suppose I take a 4-bit ADC. easy to understand what is happening. So, you have the input is coming here in the form of analog, and here is your A to D converter, and you get four of these out. Okay. So, each one of these can be either 0 or 1. Of course, these can come in serial fashion or parallel as I have shown here, just for sake of clarity. Now, what we mean is that the voltage, each input is converted an integer output. Let us see what is integer. For example, if I have 4 bits, the lowest bit is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. This is the 4 bit we talked about. For example, I can have a number like this, all zeros. Of course, the value is 0. I can have 1 here, the value is 1. I can have 2. So, if I do this, you see that the biggest number I can think of is 1111, which corresponds to 15. So, 0, 1, 2, 3 up to 15. So, there are 16 integers that are generated. That means, if the input 1 volt corresponds to the last number here 1111 all high, and 0 corresponds to 0000, the 1, 2, 3 etc. correspond to the fractions, right. So, it is like dividing the range by the number of such integers which I can represent. So, in the case of a 4 bit conversion, I only have 16 levels. So, 16 levels are there. They are also called counts. There are possibility of 16 counts. So, you can see that if I have 1 volt corresponds to the 16 counts, the least count or the it is also called the resolution is 1 over 16. That means that the steps by which I can measure the voltage is in terms of 1 over 16 volts. Count number 1 will correspond to 1 over 16 volts. So, what it means is that the digitization process introduces an error, because it will not be able to show a continuous variation, it will only show the stepwise variation. You are approximating the linear variation of the signal by a set of steps, and each step is of a unit equal to 1 over 16 in this case. But we need not of course stop with 1 over the 16 steps. In other words, 4 bits are not necessarily the only ones you can think of. You can think of larger number of steps. For example, if I have a 10 bit ADC, suppose I have a 10 bit ADC, the maximum number or maximum integer that can be represented by this is given by 2 to the power of 10 minus 1. This is nothing but the 2 to the power of bits minus 1. This is 2 to the power of n minus 1, here n is the number of bits. In this case, it will come out to be 1023. And if I include the 0, there are 1024 levels starting from the lowest value. So, suppose I have an instrument where the maximum voltage is maximum V is around 10 volts, and of course, minimum voltage 0. So, I am going to now measure these 0 to 10 volts using a 10 bit ADC, that means there are 1023, 1024 levels available. So, you can see that the resolution is equal to 1 over 2 to the power of n really is 1 over 1024, and that is the value which I am going to have, that is going to give you 0.00977. So, that is a fraction. If you multiply by multiply by the maximum value, so this is 0.0077 multiplied by the V max, and that gives you 0.007 into the 10. So, this will be something like 0.0977. Okay. So, what it means is that I think there is a small error here, let us just go through again. I am dividing the range by 1024, this is 10 divided by 10 to the power of 1024, it will be 0.0097, which is roughly equal to 0.01, roughly equal to 0.01. Actually, we can make it exactly equal to 0.01 if I choose this 10 volts a slightly higher value, which will be just nothing but 10.24 if I take, you will see that it becomes exactly equal to 0.01. That means, a 10 bit machine, 10 bit ADC can measure 10 volts in steps of 0.01, in steps of 0.01 volts. So, that is the idea. So, the point why I am discussing this is, if we are going to use a digital, if we are going to digital convert a thermocouple output to digital form, for example, if you take a thermocouple output to digital form. So, we know already that the for a thermocouple normally it is about 40 microvolts per degree Celsius. Okay. So, if I want to resolve 1 degree Celsius, I need to sense 40 microvolts. I am talking here, we were talking about 0.01 volt. So, 40 microvolts corresponds to 40 into 10 to the power of minus 6 volts. Okay, that will correspond to I have to go 4 zeros, 40 volts. This gives a 1 degree Celsius resolution. So, here we are talking about 0.01 volts, we require 10 bit. You can see that when you require this, you require many more bits than what can be got here. Okay. So, that is why modern instruments which use digital data processing use very high number of very large number of bits, and let me just show you an example which is commercially available, that is made by supplied by the National Instruments. I have taken this picture from their website. This is data acquisition. Data acquisition is one of the most important part, and National Instruments supplies a large number of data acquisition hardware and accompanied with software, and this is one of them. It is a National Instrument USB. USB means it is going to be connected to the computer to the USB port. USB is nothing but universal serial bus. Nowadays, you know, we connect the mouse to the USB, then we connect for example, a printer to the USB. We also put our pen drive and connect it to the USB So, similarly, it is possible to use this instrument data acquisition hardware by directly connecting it to the USB and then use it along with your computer. It is Windows compatible and it comes with its own driver and other software. So, you see that we can directly whatever we discussed all along now, it is all contained in this small package. It is a very small thing where the size is not bigger, much bigger than what is indicated here. It directly goes into the USB slot. And let me just give the description of this. It is a DAQ from National Instruments. It is one of the most recent additions to the National Instrument family, available very recently. It has got 4 channels and you see it has got 24-bit thermocouple input. So, you can immediately see that it is 2 to the power of 24 and you can translate it to a proper resolution value. And it also has got internal cold junction sensor, which will give a cold junction compensation. So, you do not require a reference temperature junction to be maintained. It is done by actually sensing the cold junction temperature or the room temperature and correcting for it, and it is compatible with all the different thermocouples which we have described earlier, J, K, R, S, T, name it and it is here. So, all you have to do is to the software will take care of it. All you have to do is to tell from using the software to find out to specify which thermocouple has been used in your particular measurement, and then automatically it will take care of it, and it is plug and play connected with USB. That means it automatically be recognized by Windows and it will be driver is almost like it is already there, and is powered by the bus. So, you do not have external power supply to be hooked onto it, and in fact it is available in Windows 2000 XP or also Mac and Linux versions, and the one I showed in the previous here, it is the Windows version. For the other one they have a simple slightly different version, and the software is also supplied by the National Instruments. So, just to see the resolution we are talking about, resolution of 1 over 2 to the power 24 is 5.96 10 minus 8, it is something like approximately 0.1 microvolts per volt. So, you see that we are now talking about measuring very small voltage levels. Obviously, the instrument which I just now showed, it must have its own amplification, it must have its own manipulation. All the items which I mentioned are already built into this 9211. So, you do not have to connect anything specifically to that, it is already there, and the software will take care of the most of the things. And as I said earlier, the software which comes with National Instruments is the LabVIEW. So, if you look at the LabVIEW software, with LabVIEW you can design the appearance of the instrument. That means that the PC monitor will show the front of the instrument. For example, you can have a temperature measuring recording window in which the variation of the temperature will be shown by a graphical representation, or you can have a small window in which the actual temperature will be displayed, and things like that. This can be designed by using what is called the LabVIEW software, and it has got various facilities, and if one understands how to use the LabVIEW, one would be able to make the entire thing looks like actually real instrument. That is why it is called virtual instrument. Virtual instrument means it looks like a real one, but it is actually virtual, because nothing is physically there, it is only the software which is doing it. For example, I can make an oscilloscope, and the oscilloscope will show up on your PC monitor, and you can actually use your mouse and then make adjustments, and because it is behind the whatever we see in the monitor, there is a program which is running, and the program is controlled by the user input through the windows, through the buttons and so on, and that it is as though you are actually operating an instrument, but actually done by using a virtual instrument on your console or in your PC monitor. You see that one. So, this is the latest development which I thought would be useful for people to know. So, to to go back to the board, let us just recapitulate what we are talking about. We have the sensor, then signal conditioning, and then we have ADC, we have the computer. The connection in this case is through USB, that is what we just now mentioned. Earlier we used to have what is called GPIB or general purpose instrument bus, or it could be through a serial connection, serial port. So, these are all possible ways of communicating with the computer. So, this portion, or at least this portion, can be in the form of a board. When I say a board, it is a printed circuit board or a PCB. In many of the versions of the National Instruments supplied hardware, this comes in the form of a board which goes into a slot. Board goes into a slot in the computer itself. So, the signal conditioning and signal data acquisition board can become actually a part of your computer. It can be put inside, or in the new version, as we have seen, it could be USB connected. That means, it connects to one of the USB ports available on the computer, so that you do not have to really make any changes within the computer itself. So, you do not have to open the back of the computer and put the board inside and so on. That is avoided, because it can be kept outside. So, this is generally what happens nowadays when you have a laboratory, and when you want to set up a laboratory, you can go for, instead of buying all the separate things and putting together, one can simply buy some of these ready made equipment available, and then we can make the measurement very easily. They are also available in the following form, which we call as the data loggers. For example, the Hewlett Packard supplies large number of data loggers of different types. So, these data loggers are standalone or connected to computer. Both ways you can do. That means, they have some memory of their own, so that you can save the data and you can download it to the computer later on if you want to make any analysis. And these data loggers come with several channels, several input channels, and maybe several output channels also, so that you can run, or you can use the computer to control some experiment. So, those are also possible. So, I think in this lecture we have been able to sort of give an overview of what is required for running a laboratory, understanding how to make a choice of an instrument and so on. So, what we will do in the concluding lecture, which is going to come as lecture number 50, would be to take one or two simple cases where we can actually look at how we are going to design the required hardware, or choose the desired hardware for performing a particular experiment. We will try to do it in the last lecture, which is going to follow. Thank you.